Muḥammad ibn Mūsā with Macron Al-Khwarizmi, Arabic, c. 780 c. 850, Arabic pronunciation, ælxɑːræzmiː, formerly Latinized as Algoritmi, was a Persian mathematician, astronomer, and geographer during the Abbasid Caliphate, a scholar in the House of Wisdom in Baghdad. In the 12th century, Latin translations of his work on the Indian numerals introduced the decimal positional number system to the Western world. Al-Khwarizmi, the compendious book on calculation by completion and balancing, presented the first systematic solution of linear and quadratic equations in Arabic. In Renaissance Europe, he was considered the original inventor of algebra, although it is now known that his work is based on older Indian or Greek sources. He revised Ptolemy's geography and wrote on astronomy and astrology. Some words reflect the importance of Al-Khwarizmi's contributions to mathematics. Algebra is derived from algebra, one of the two operations he used to solve quadratic equations. Algorithm and algorithm stem from Algoritmi, the Latin form of his name. His name is also the origin of Spanish, guarismo, and of Portuguese, algarismo, both meaning digit. Few details of Al-Khwarizmi's life are known with certainty. He was born in a Persian family, and Ibn al-Nadim gives his birthplace as Khwarizm in Greater Khorasan, modern Khorasan region, Uzbekistan. Muhammad ibn Jarir al-Tabari gives his name as Muhammad ibn Musa al Khwarizmi al-Mahsi al-Karabali. The epithet al-Katrabuli could indicate he might instead have come from Katrabul, a viticulture district near Baghdad. However, Rashid suggests there is no need to be an expert on the period or a philologist to see that al-Tabari's second citation should read Muhammad ibn Musa al-Khwarizmi and al-Mahsi al-Katrabuli, and that there are two people, al-Khwarizmi and al-Mahsi al-Katrabuli, between whom the letter wa Arabic for the conjunction end has been omitted in an early copy. This would not be worth mentioning if a series of errors concerning the personality of Al-Khwarizmi, occasionally even the origins of his knowledge, had not been made. Recently, G.J. Toomer, with naive confidence, constructed an entire fantasy on the error which cannot be denied the merit of amusing the reader. Regarding Al-Khwarizmi's religion, Toomer writes, another epithet given to him by Al-Abar, al-Mahz, would seem to indicate that he was an adherent of the old Zoroastrian religion. This would still have been possible at that time for a man of Iranian origin, but the pious preface to Al-Khwarizmi's Algebra shows that he was an Orthodox Muslim, so Al-Abar's epithet could mean no more than that his forebears, and perhaps he in his youth, had been Zoroastrians. Ibn al-Nadm's Kitb al-Firayst includes a short biography on Al-Khwarizmi together with a list of the books he wrote. Al-Khwarizmi accomplished most of his work in the period between 813 and 833. After the Muslim conquest of Persia, Baghdad became the center of scientific studies and trade, and many merchants and scientists from as far as China and India traveled to this city, as did Al-Khwarizmi. He worked in Baghdad as a scholar at the House of Wisdom established by Caliph al-Ma'mun, where he studied the sciences and mathematics, which included the translation of Greek and Sanskrit scientific manuscripts. Douglas Morton Dunlop suggests that it may have been possible that Muhammad ibn Mūsā with Macron Al-Khwarizmi was in fact the same person as Muhammad ibn Mūsā with Macron ibn Shkr, the eldest of the three Ban Mūsā with Macron. Al-Khwarizmi's contributions to mathematics, geography, astronomy, and cartography established the basis for innovation in algebra and trigonometry. His systematic approach to solving linear and quadratic equations led to algebra, a word derived from the title of his 830 book on the subject, the compendious book on calculation by completion and balancing. On the calculation with Hindu numerals written about 825, was principally responsible for spreading the Hindu Arabic numeral system throughout the Middle East and Europe. It was translated into Latin as Algoritmi de numero inderum. Al-Khwarizmi, rendered as Latin, Algoritmi, led to the term algorithm. Some of his work was based on Persian and Babylonian astronomy, Indian numbers, and Greek mathematics. Al-Khwarizmi systematized and corrected Ptolemy's data for Africa and the Middle East. Another major book was Kitab Surat al-Ard, the image of the earth, translated as geography, presenting the coordinates of places based on those in the geography of Ptolemy but with improved values for the Mediterranean Sea, Asia, and Africa. He also wrote on mechanical devices like the astrolabe and sundial. He assisted a project to determine the circumference of the Earth and in making a world map for Al-Ma'mun, the Caliph, overseeing 70 geographers. When, in the 12th century, his works spread to Europe through Latin translations, it had a profound impact on the advance of mathematics in Europe. The compendious book on calculation by completion and balancing, Arabic, Al-Kitb al-Mukhtar f-Isib al-Jabr wal-Muqbala, is a mathematical book written approximately 830 CE. The book was written with the encouragement of Caliph al-Ma'mun as a popular work on calculation and is replete with examples and applications to a wide range of problems in trade, surveying and legal inheritance. The term algebra is derived from the name of one of the basic operations with equations, al-Jabr, meaning restoration, referring to adding a number to both sides of the equation to consolidate or cancel terms, described in this book. The book was translated in Latin as Liber Algebrae et al-Muqabala by Robert of Chester, Segovia, 1145, hence algebra, and also by Gerard of Cremona. A unique Arabic copy is kept at Oxford and was translated in 1831 by F. Rosen. A Latin translation is kept in Cambridge. It provided an exhaustive account of solving polynomial equations up to the second degree 16 and discussed the fundamental methods of reduction and balancing, referring to the transposition of terms to the other side of an equation, that is, the cancellation of like terms on opposite sides of the equation. Al-Khwarizmi's method of solving linear and quadratic equations worked by first reducing the equation to one of 6 standard forms, where b and c are positive integers. Squares equal roots, ax2 equals bx. Squares equal number, ax2 equals c. Roots equal number, bx equals c. Squares and roots equal number, ax2 plus bx equals c. Squares and number equal roots, ax2 plus c equals bx. Roots and number equal squares, bx plus c equals ax2. By dividing out the coefficient of the square and using the two operations al-Jabr, Arabic, restoring or completion, and al-Muqbala, balancing. Al-Jabr is the process of removing negative units, roots, and squares from the equation by adding the same quantity to each side. For example, x2 equals 40x, 4x2 is reduced to 5x2 equals 40x. Al-Muqbala is the process of bringing quantities of the same type to the same side of the equation. For example, x2 plus 14 equals x plus 5 is reduced to x2 plus 9 equals x. The above discussion uses modern mathematical notation for the types of problems which the book discusses. However, in Al-Khwarizmi's day, most of this notation had not yet been invented, so he had to use ordinary text to present problems and their solutions. For example, for one problem he writes, from an 1831 translation. If someone say, you divide 10 into 2 parts, multiply the one by itself, it will be equal to the other taken 81 times. Computation, you say, 10 less thing, multiplied by itself, is 100 plus a square less 20 things, and this is equal to 81 things. Separate the 20 things from 100 and a square, and add them to 81. It will then be 100 plus a square, which is equal to 101 roots. Have the roots, the moiety is 50 and a half. Multiply this by itself, it is 2550 and a quarter. Subtract from this 100, the remainder is 2450 and a quarter. Extract the root from this, it is 49 and a half. Subtract this from the moiety of the roots, which is 50 and a half. There remains 1, and this is one of the 2 parts. Several authors have also published texts under the name of Kitb al-Jabr wal Muqbala, including Ibn Fadinawar, Ab Kamil Shujai ibn Aslam, Ab Muhammad al-Adl, Ab Ishav al-Mi, Abd al-Hamd ibn Turk, Sind ibn Nil, Saul ibn Bir, and Sharaf al-Din al-S. J. J. O'Connor and E. F. Robertson wrote in the MacTutor History of Mathematics Archive. Perhaps one of the most significant advances made by Arabic mathematics began at this time with the work of al-Khwarizmi, namely the beginnings of algebra. It is important to understand just how significant this new idea was. It was a revolutionary move away from the Greek concept of mathematics, which was essentially geometry. Algebra was a unifying theory which allowed rational numbers, irrational numbers, geometrical magnitudes, etc., to all be treated as algebraic objects. It gave mathematics a whole new development path, so much broader in concept to that which had existed before, and provided a vehicle for future development of the subject. Another important aspect of the introduction of algebraic ideas was that it allowed mathematics to be applied to itself in a way which had not happened before. R. Rashid and Angela Armstrong write, Al-Khwarizmi's text can be seen to be distinct not only from the Babylonian tablets, but also from Diophantus Arithmetica. It no longer concerns a series of problems to be resolved, but an exposition which starts with primitive terms in which the combinations must give all possible prototypes for equations, which henceforward explicitly constitute the true object of study. On the other hand, the idea of an equation for its own sake appears from the beginning and, one could say, in a generic manner, insofar as it does not simply emerge in the course of solving a problem, but is specifically called on to define an infinite class of problems. Al-Khwarizmi's second major work was on the subject of arithmetic, which survived in a Latin translation but was lost in the original Arabic. The translation was most likely done in the 12th century by Adelard of Bath, who had also translated the astronomical tables in 1126. The Latin manuscripts are untitled, but are commonly referred to by the first two words with which they start, Dixit Algoritmi, so said Algorithm, or Algoritmi de numero inderum, Algorithm on the Hindu art of reckoning, a name given to the work by Baldassare Boncompagni in 1857. The original Arabic title was possibly Kitb al-Jamwat Tafriq by Asib al-Hind, the book of addition and subtraction according to the Hindu calculation. Al-Khwarizmi's work on arithmetic was responsible for introducing the Arabic numerals, based on the Hindu Arabic numeral system developed in Indian mathematics, to the Western world. The term algorithm is derived from the algorithm, the technique of performing arithmetic with Hindu Arabic numerals developed by Al-Khwarizmi. Both algorithm and algorithm are derived from the Latinized forms of Al-Khwarizmi's name, Algoritmi and Algoritmi, respectively. Al-Khwarizmi's Zj al-Sind Hind, Arabic, Astronomical Tables of Sind and Hind, is a work consisting of approximately 37 chapters on calendrical and astronomical calculations and 116 tables with calendrical, astronomical, and astrological data, as well as a table of sign values. This is the first of many Arabic zijas based on the Indian astronomical methods known as the Sind Hind. The work contains tables for the movements of the Sun, the Moon, and the 5 planets known at the time. This work marked the turning point in Islamic astronomy. Hitherto, Muslim astronomers had adopted a primarily research approach to the field, translating works of others and learning already discovered knowledge. The original Arabic version, written c. 820, is lost, but a version by the Spanish astronomer Maslama ibn Ahmad al-Majriti, c. 1000, has survived in a Latin translation, presumably by Adelard of Bath, January 26, 1126. The 4 surviving manuscripts of the Latin translation are kept at the Bibliothèque Publique, Chartres, the Bibliothèque Mazarine, Paris, the Bibliothèque Nacional, Madrid, and the Bodleian Library, Oxford. Trigonometry. Al-Khwarizmi's Zj al-Sind Hind also contained tables for the trigonometric functions of sines and cosine. A related treatise on spherical trigonometry is also attributed to him. Al-Khwarizmi's third major work is his Kitb al-Ar, Arabic, Book of the Description of the Earth, also known as his Geography, which was finished in 833. It is a major reworking of Ptolemy's 2nd century geography, consisting of a list of 2,402 coordinates of cities and other geographical features following a general introduction. There is only one surviving copy of Kitb al-Ar, which is kept at the Strasbourg University Library. A Latin translation is kept at the Biblioteca Nacional de España in Madrid. Citation needed. The book opens with the list of latitudes and longitudes, in order of weather zones, that is to say in blocks of latitudes and, in each weather zone, by order of longitude. As Paul Gallés Dubius Discuss points out, this excellent system allows the deduction of many latitudes and longitudes where the only extant document is in such a bad condition as to make it practically illegible. Neither the Arabic copy nor the Latin translation include the map of the world itself. However, Hubert Donnecht was able to reconstruct the missing map from the list of coordinates. Donnecht read the latitudes and longitudes of the coastal points in the manuscript, or deduces them from the context where they were not legible. He transferred the points onto graph paper and connected them with straight lines, obtaining an approximation of the coastline as it was on the original map. He then does the same for the rivers and towns. Al-Khwarizmi corrected Ptolemy's gross overestimate for the length of the Mediterranean Sea 27 from the Canary Islands to the eastern shores of the Mediterranean. Ptolemy overestimated it at 63 degrees of longitude, while Al-Khwarizmi almost correctly estimated it at nearly 50 degrees of longitude. He also depicted the Atlantic and Indian Oceans as open bodies of water, not landlocked seas as Ptolemy had done. Al-Khwarizmi's prime meridian at the Fortunate Isles was thus around 10 degrees east of the line used by Marinus and Ptolemy. Most medieval Muslim gazetteers continued to use Al-Khwarizmi's prime meridian. Jewish calendar. Al-Khwarizmi wrote several other works including a treatise on the Hebrew calendar, titled Risla fi Istikraj Ta'arkh al-Yad, Arabic, Extraction of the Jewish Era. It describes the Medinic cycle, a 19-year intercalation cycle, the rules for determining on what day of the week the first day of the month Tishrei shall fall, calculates the interval between the Anno Mundi or Jewish year and the Seleucid era, and gives rules for determining the mean longitude of the sun and the moon using the Hebrew calendar. Similar material is found in the works of Ibrahim al-Bi'aran and Maimonides. Other works. Ibn al-Nadim's Kitb al-Khwarizmi, an index of Arabic books, mentions Al-Khwarizmi's Kitb al-Tarikh, Arabic, a book of annals. No direct manuscript survives, however. A copy had reached Nasibin by the 11th century, where its metropolitan bishop, Mar Ilyas bar Shiniya, found it. Elias's chronicle quotes it from the death of the prophet through to 169 AH, at which point Elias's text itself hits a lacuna. Several Arabic manuscripts in Berlin, Istanbul, Tashkent, Cairo, and Paris contain further material that surely or with some probability comes from Al-Khwarizmi. The Istanbul manuscript contains a paper on sundials. The Khwarizmi credits Al-Khwarizmi with Kitb ar-Rukma, t. Arabic. Other papers, such as one on the determination of the direction of Mecca, are on the spherical astronomy. Two texts deserve special interest on the morning width. Marifat Essay at al-Mashriq f Kul Balad, and the determination of the azimuth from a height, Marifat al-Samt min Qibal al-Irtif. He also wrote two books on using and constructing astrolabes. Algebra is derived from Algebra, one of the two operations he used to solve quadratic equations. Algorithm and algorithm stem from Algoritmi, the Latin form of his name. His name is also the origin of Spanish, Guarismo, and of Portuguese, Algarismo, both meaning digit. Few details of Al-Khwarizmi's life are known with certainty. He was born in a Persian family, and Ibn al-Nadim gives his birth. Tabari's second citation should read Muḥammad ibn Mūsā al-Khwarizmi and al-Muḥsī al-Khatrabuli, and that there are two people, Al-Khwarizmi and al-Muḥsī al-Khatrabuli, between whom the letter wa Arabic for the conjunction end has been omitted in an early copy. This would not be worth mentioning if a series of errors concerning the personality of Al-Khwarizmi, occasionally even the origins of his knowledge, had not been made. Recently, the place as Khwarizm in Greater Khorasan, modern Khwarazm region, Uzbekistan. Muhammad ibn Jarir al-Tabari gives his name as Muhammad ibn Musa al-Khwarizmi al-Muḥsī al-Khatrabuli. The epithet al-Khatrabuli could indicate he might instead have come from Khatrabul, a viticulture district near Baghdad. However, Rashid suggests there is no need to be an expert on the period or a philologist to see that Muhammad ibn Musa with Makron al-Khwarizmi, Arabic, c. 780 c. 850, Arabic pronunciation, ælxɑːræzmiː, formerly Latinized as Algoritmi, was a Persian mathematician, astronomer, and geographer during the Abbasid Caliphate, a scholar in the House of Wisdom in Baghdad. In the 12th century, Latin translations of his work on the Indian numerals introduced the decimal positional number system to the Western world. Al-Khwarizmi, the compendious book on calculation by completion and balancing, presented the first systematic solution of linear and quadratic equations in Arabic. In Renaissance Europe, he was considered the original inventor of algebra, although it is now known that his work is based on older Indian or Greek sources. He revised Ptolemy's geography and wrote on astronomy and astrology. Some words reflect the importance of Al-Khwarizmi's contributions to mathematics.